Hello students, how are you? Welcome back to my YouTube channel Physics Insight. In this video we are going to discuss about the wave nature of light. In today's lecture we are going to study about wavefronts, then we will discuss about Huygen's principle, then laws of reflection and refraction using wave theory, and after that we are proceeding to the section of interference. Now proceeding to the first topic, that is wavefront. So we define wavefront as locus of all the particles of a medium which at any instant are vibrating in the same phase is called wavefront. So what does the term locus stands for? So locus is a set of all points which satisfies a given condition. Okay, so how you will define this point locus diagrammatically? For example, if we take an example of a circle, so what will be the locus of this circle? See, locus of this circle is all the points which are at equal distance. Because this is the property of circle, that all the points lying on the periphery of circle are at equal distance from the center. Okay. So I hope the definition of wavefront is clear to you. Now it will be more clear to you once we are switching to the types of wavefronts. So we are having following types of wavefronts depending on shape of source of light. So firstly we are going to discuss spherical wavefront. So spherical wavefront is produced by a point source it is because the locus of all such points which are equidistant from point source is a sphere. Okay, so that's why the type of wavefront generated by a point source is spherical wavefront. So how it looks like, see, this is my point source. So these are the points which are at equal distance. Okay, actually this point source is sending vibrations in phase in all the directions. So means all the particles are covering the same distance. So this periphery which we have obtained by joining all these equidistant points is named as a wavefront. So this periphery which I am going to draw now represents a spherical wavefront. Okay, so now proceeding to the cylindrical wavefront. When source of light is in linear shape, a cylindrical wavefront is formed. It is because all the points which are equidistant from a linear source lie on the surface of a cylinder. For example, this is my linear source. So all the points which are equidistant from this linear source lie on the surface of this cylinder. So the vibrations generated by the top and bottom end will lie on this part, and the vibrations generated by the flat surface will lie on this path. Okay, so they will be like presenting on the surface of a cylinder. So the wavefront generated by a plane source is cylindrical wavefront. I hope this is clear to you. Next, the third type which we are dealing is now a plane wavefront. When a small part of spherical or cylindrical wavefront originates from a distant source, it will appear as a plane and hence it is called a plane wavefront. For example, like a spherical wavefront is coming from a far lying point source. So as traveling the distance, so it starts becoming flat because radius of curvature is becoming more and more as the vibrations travel a longer distance. So this will get converted into a flat surface. So this is what we call as plane wavefront. So same is the case with the extended source of cylindrical wavefront. Both of them will get converted to automatically plane wavefront. So this is how a plane wavefront looks like, just like a straight line. Next we are dealing with the ray of light. Simply an arrow drawn normal to the wavefront and pointing the direction of light. So we name that arrow as ray of light. Also, since ray of light is normal to the wavefront, so it is also sometimes called as wave normal. So just see how my ray of light appears normal to the wavefronts. For first time I am dealing with the plane wavefront. See, this is my plane wavefront. Okay. So now I am going to draw perpendicular to it. So these lines which I am drawing horizontally, so they are perpendicular on the wavefront. So they indicates ray over a plane wavefront. So now proceeding to the spherical wavefronts. So spherical wavefronts can be of two types, either of this kind. So here the ray will be perpendicular in such a way. Like this. So this is the direction of ray. And if spherical wavefront is in this direction, like this, then ray of light will be like this, 90 degree along the direction of propagation. Okay, if the direction of propagation is like this, the ray will be drawn like this. Any confusion in this? I hope the concept of ray of light and how it is related to wavefront is clear to you. So next I am showing you the different wavefronts for the following objects, or you can say that after refraction how wavefront changes. See, here in case of convex lens we have incidented a spherical wavefront. See, when object is located at the focus of this convex lens, so after getting refracted, all these rays which are coming from focus goes parallel to each other, hence they emit a plane wavefront. Okay, so your spherical wavefront gets converted to plane wavefront after refraction through convex lens. Now if you will incident a plane wavefront on a convex lens, so automatically it will get converted to spherical wavefront because all these rays will converge at point F. In case of concave lens, if you will incident a plane wavefront, so they will get converted into a spherical wavefront. Now in case of prism, if you will incident a plane wavefront on the first phase, so from the emerging out phase, you will again receive a plane wavefront. Now let's talk about some mirrors also, that in mirrors what will happen? Like lenses, mirrors will also behave same. See, if you will incident a plane wavefront on a convex mirror, so this is the incident surface. This is the incident surface. So if you will incident plane wavefront over here, so after reflection, that plane wavefront will get converted into the spherical wavefront. Now in case of concave mirror also, again the plane wavefront gets converted to spherical wavefront. But in case of plane mirror, if you will incident a plane wavefront, so after reflection you will again obtain a plane wavefront. So these structures you can get in exam for 1 marks, that draw the refracting or reflecting wavefront for the given figure. Okay. So next, proceeding for the Huygen's principle. So this principle states that every point on primary wavefront, or you can say every point on given or primary wavefront, acts as source of secondary wavelet. sending out disturbance in all directions. In similar manner. And all these wavelets move with speed of light. Then third, the new position of wavefront at any instant is enveloped to secondary wavelets at that instant. Now understand these three things from a simple diagram. See, this is my given wavefront, or you can say this is my primary wavefront. So every point on this primary wavefront has tendency to generate a secondary wavelet. So this point has generated this wavelet, this wavelet, this wavelet, this wavelet, and this wavelet. So how will you get the new position of the wavefront? Just draw a tangent over these wavelets. So you will get a new wavefront, okay, so which is called secondary wavefront. So now see this secondary wavefront. These are secondary wavelets. So this secondary wavefront is acting as an envelope for these secondary wavelets. So envelope, we very well understand that envelope is used to hide the letter inside. So here your secondary wavefront is covering your secondary wavelets. This is how it acts as an envelope for the secondary wavelet. Clear? Now proceeding for the next topic. We are going to discuss the laws of refraction using wave theory. Earlier we very well know in the junior classes that laws of refraction states that incident ray, refracted ray and normal all lie in same plane, and second law is the ratio of sine of angle of incidence to the sine of angle of refraction is constant, that is refractive index. Okay, so we are going to verify these two laws using wave theory. Now clearly understand, first of all we are assuming a situation that here we are having two rays which are incidenting on a refracting interface x and x dash. Okay, so this is my refracting interface on which my two rays are incidenting. So this AB is my incident wavefront and this is my refracting wavefront and this is my refracting ray. This is refracted ray, and see I have indicated the angle made by incident wavefront with the interface as I and angle made by the refracting wavefront with the interface as R. So how these things I have plotted? Just see, here we very well know that angle of incidence is the angle made by normal with the incident ray. Okay, so this is my I. Now I indicate the angle made by my wavefront with the interface Bx. Okay, so clearly my wavefront is normal to the ray. So this complete angle is equal to 90 degree. Then this angle between wavefront and the normal can be written as 90 minus I, because this first angle is I. So this angle between wavefront and normal is 90 minus I. Now just check the angle between normal and interface. So this will be 90 minus I plus x is equals to 90 degree, because normal is at 90 degree to the interface. So this 90 degree is representing the angle between normal and interface. Now see, this 90 will cancel with this 90. So the value of x will directly came out to be I. So automatically where I have plotted x in the diagram, so that can be replaced by symbol I. Okay, similarly, the angle made by the refracting wavefront with the interface is R. Now we will find out the value of sin I from the diagram. So see, this is a right angle triangle. First of all, this is a right angle triangle. So in right angle triangle, if we apply trigonometry, so we consider the angle between base and hypotenuse. So this is your perpendicular, this is your base, and this is your hypotenuse. Clearly in this is your base, this is your hypotenuse, and this is your perpendicular. Okay. So now in triangle ABC, sin I is given by perpendicular is BC upon hypotenuse is AC. Now in triangle ADC, sin R is given by perpendicular is AD and hypotenuse is AC. Now evaluate sin I by sin R. So it is BC upon AC upon AD upon AC. Now AC cancels out, so you will be left with BC upon AD. Okay, so now sin I is BC by AD. So clearly this BC is the distance and AD is again the distance. If V1 is the velocity of wave in medium 1, so this distance can be written as velocity into time, because the time taken by the wave from point B to C is equals to the time taken by a wave to reach from point A to D. Okay, so this can be written as V to D and V1t. So this again, time being same, will cancel out each other. So here we will get the ratio of V1 by V2. So which is nothing but the refractive index. As per the definition of refractive index, it is the speed of light in two different mediums. Ratio of speed of light in one medium to the ratio of speed of light in second medium. So which is nothing but just a Snell's law, the second law of refraction. And moreover, clearly it is indicated in the diagram that normal, incident and refracted ray all lie in same plane. In this way we have verified both the laws of refraction. Now in the similar way we will verify the laws of reflection. Now we are going to verify the laws of reflection using wave theory. Here we are considering a reflecting wavefront dash on which we are incidenting two parallel rays such that after reflection the ray which is incidenting at point A will follow the path AD, and the ray BC which will incident on the interface will emerge out from the point C as shown in diagram. So here AB is indicating the incidenting plane wavefront and CD is indicating the reflecting wavefront. Moreover, we are assuming here that the time taken by the wave coming from point B is reaching at point C. At the same time, the ray starting from point A will reach at the point D as per the Huygen's theory. Okay, and moreover, now we are concerned with this angle made by this plane wavefront with the interface. So we are assuming this angle to be x. Since this is my normal and this is the angle made by normal with incident ray, that is angle I, and thus angle made by normal with the incident wavefront will be 90 minus I. Why? Because this wavefront is at 90 degree to this ray. Okay, so this complete angle will be 90 degree, hence this small portion will be 90 minus I. Also, since this normal is at 90 degree to the interface, or you can say that to this reflecting interface, so this 90 minus I plus x will be equal to 90 degree. So from here 90 cancels with this 90 and x came out to be I. So from here we are getting that my incident wavefront is making angle I with this reflecting interface. Similarly, my reflecting interface will make angle with this reflecting wavefront to be R. Now taking two triangles, in triangle ABC and in triangle ADC, angle B and angle D both are equal as each is equivalent to 90 degree. Next, AC and AC are common. Moreover, BC and AD is equal to CD, as we have taken that time taken by the ray to reach from point B to C is equal to time taken by the wavelet to reach from point A to D. So this we have considered here. So that's why BC and AD equal to CT. Now by RHS rule, both the triangles, triangle ABC is congruent to triangle BDC. Okay, this ABC and ADC. Congruent to triangle ADC. So by CPCT, angle I will be equal to R, which is the second law of reflection. Okay. Now clearly, as we look into the diagram carefully, so we will see that incident ray, normal and reflected wave all are lying in same plane. Thus, this is my first law of reflection. So in this way, we have verified the law of reflection using wave theory also. Next, moving to the further topics. Now we are starting with the interference. So what do you mean by the term interference? In the physics, we call this interference as the combination of two or more electromagnetic waveforms to form a resulting wave. Now in order to understand more scientific information, let's go in depth and let's study superposition principle first. In the class +1, you must have studied this principle, superposition principle. So now we are giving you a short review using a simple definition, that when two or more waves travels simultaneously in a medium, the resultant displacement at each point of medium at any instant is equal to the sum of displacements produced by two waves. Okay, for example, अब मैं आपको इसको डायग्रामेटिकल वे से समझाने की कोशिश करता हूं. Like we are having two waves. See, this is my one wave in which we are having crest, 3 units of crest and 2 units of trough. And if we superimpose it, another wave traveling in the same position, that is having in time period 0 to 1 second, again 2 units crest and 1 unit trough. So now the resultant wave will be in the same time interval 0 to 1 second in such a way that it will be having 5 units of amplitude of crest, and in trough you will be having 3 units. Okay, and what if your wave is having some phase difference, like if we are having one wave in such a way and another way in such a way, so their amplitudes will get subtracted because direction is reversed. Now crest is getting overlapped with the trough and trough is getting overlapped with the crest, so the net resultant amplitude will be after subtraction. You will get it after subtraction. It will be smaller in amount. Here why we have shown it crest first, because in the first wave crest is bigger as compared to trough. Okay, so that's why in the first half cycle we are getting crest here. So if both of these having same amplitudes for crest and trough, so you will get nothing. There will be complete darkness, nothing will be shown there. Okay, so from here, after getting this principle, so this is somewhat we will apply an interference. So how will you define interference? So we will say that the redistribution, it is the redistribution of light intensity or amplitude, you can say, due to superposition of two waves, okay, is called interference. So this is the actual definition of interference. Now here we have written intensity, but actually in the superposition principle the amplitudes were varying. So clearly we very well know that intensity is proportional to amplitude square. That's why if amplitude will vary, also intensity will vary. So your resultant wave will have a different intensity as compared to the incident ones. I hope it is clear to you. Now after this interference, we are going to proceed for the Young's double slit experiment. Okay. So for Young's double slit experiment, what are the conditions we need for the interference pattern to obtain on a screen? First condition is two sources should emit light waves continuously. This is first condition. The same condition we will proceed with the next. वो सेम वाली कंडीशन हम नेक्स्ट इसके बाद लिखते हैं. टू सोर्सेज शुड एमिट लाइट वेव्स कॉन्टिन्यूसली. आफ्टर दैट light waves should be of same wavelength. Next, light waves emitted should preferably of same amplitude. The next condition, that is waves emitted by two sources either in same phase or should have a constant phase difference. Now next condition, the fifth one is two sources of light must lie close to each other. Then next one, two light sources should be narrow. These 6 conditions our sources should follow for getting any interference pattern. Okay. So next, proceeding for the Young's double slit experiment ahead. So here what we need two similar sources which should emit the same wavelength, constant phase difference. So all of these properties are difficult to follow by two separate sources. So what we are doing, we are taking a common source S. So further we are making two different sources from this. which are similar in nature. So S1 and S2 are similar to each other. So see clearly, this is my emerging wavefront. From here my secondary wavelets are generating. So when the wavelets are hitting the slit at point S1 and S2, so S1 and S2 are two slits. When my incident wavefronts hit here, so this will exist as a source of secondary wavelets, and further these you can say wavelets go on from S1 and S2. When wavelets generated by these two sources S1 and S2 will interfere with each other, so you will get interference pattern on the screen. So we have shown this. So here we have marked with the 2 points, one is minima and one is maxima. So when you will get minima on the screen, minima means the darkness, okay, and maxima means the maximum intensity, the bright one. So fringes are obtained like this: dark fringe, then bright fringe, then again dark fringe, again bright fringe. Alternatively these fringes are so obtained. So when these fringes are obtained, we very well know that light travels in the form of crest and troughs, okay. So what we can do, we can mark these crests and trough with the dark solid lines and with the dotted lines. So when here I am indicating with the dark line crest and with the dotted one the trough. So when trough overlaps with the trough and crest overlap with the crest, means crest of first source is interfering with the crest of other source, or trough of first source is interfering with the trough of other source. So in this case constructive interference takes place. In this constructive interference takes place and you will get maxima. While when crest of, see in the next cycle, so this is crest, so it is here also for this is crest. Now see here crest of one source is emerging with the trough of other source. So when crest and trough overlaps, crest of one source is overlapping with the trough of other source, so you will get destructive interference. And from here what you will get, a dark band is formed. Okay, so dark band is formed, means there is no light at all on the screen in that particular region. Why so? Because both crest and trough are having same amplitudes. If crest of same amplitude overlaps with the trough of same amplitude, so they will cancel out each other's effect. Okay, so I am going to show one animation that how this process is taking place. Just focus here. Now see, here we are having two sources S1 and S2. Okay, so here are my wavelets which are moving. So let me show you how they travel. So this is how they will move. So these are the secondary wavelets which are being generated from the sources S1 and S2. Once they are traveling, so they are interfering with each other. So you can see crests are overlapping, or you can say troughs are overlapping. Okay, so I have not plotted the troughs here. So trough you can plot it like a dotted wave. Okay, so with solid line we can represent a crest, again like this. Alternatively you can draw. Okay, so then you will analyze where this trough and crest will overlap. You will get a minima. So where the crest of these two sources is overlapping, so you will get a maxima there. So this is the pattern of fringes which you will obtain on the screen. See, when two crests are overlapping, so corresponding to these crests, you are getting a bright fringe here, like this, bright fringe, like this, bright fringe, like this, a bright fringe. So where there is trough and crest, so you will get a dark band here, like this. Okay, so this is how you will get alternate bright and dark fringes. I hope the experiment, Young's double slit experiment, is clear to you. Now we are going to evaluate the fringe width, means the distance between these two fringes, the distance between these two bright fringes, the distance between these two dark fringes. Okay, so we are going to evaluate this mathematically now. The situation is indicated by the source S1 and by the source S2. So clearly you can see from the diagram the rays emerging out from the point S1 is traveling the shorter distance as compared to S2P. Okay. What will be the path difference between the wavelets originating from point S1 and from point S2? So that we can write it as path difference will be S2 minus S1P. So in diagram, what we will indicate it? See, we are drawing one perpendicular from this point S1 on the wave originating from this S2. So this gap is indicated by this symbol delta. Now the condition is, firstly we have to evaluate this path difference. So let's begin from the right angle triangle S1PM. In triangle S1PM, hypotenuse square is equals to base square plus perpendicular square. So what is the value of S1M? This is D, capital D. So D square plus, now what is the value of this MP? Clearly, if the gap between S and S2 is D, and moreover these slits S1 and S2 are at equal distance from this point Q, so this distance will be D by 2 and also this distance will be D by 2. So the value of PM can be evaluated by subtracting D by 2 from Y. So what will be the value then? So we can write this value to be Y minus D by 2 square. Similarly, S2P square can be represented by S2N square plus NP square. So it can be written as D square plus Y plus D by 2 square. Okay. So now let's subtract these two. S2P square minus S1P square. So what you will get? Once you will subtract, so you will be left only with Y plus D by 2 square minus Y minus D by 2 whole square. So you will be left with this. Here we can write S2P square minus S1P square and will be equal to, once you will open these brackets with the formula of A plus B whole square and A minus B whole square, so you will be left with only 2YD here. Okay. Now let's apply the formula A square minus B square here. So it will be S2P plus S1P, S2P minus S1P is equals to 2YD. Any confusion in this? I hope this much content is clear to you. We have obtained S2P plus S1P and S2P minus S1P equal to 2YD. Okay. So now we are assuming, say point P lies close to O. Then these distances S1P, S2P, these will be equal to your D, approximately equal to D, because all these points are approximately equal to क्या हुआ? Okay. So then the above expression will be reduced to D plus D. So this S2P minus S1P, we have indicated it with path difference, or we are naming it with delta. This is my path difference. So it will be 2YD. Now 2D is equals to 2D into delta is equals to 2YD. Now 2 cancels with this 2. So delta will be equal to YD by D. So this is the path difference between the wavelets originating from S1 and wavelets originating from S2. Now we will apply certain conditions in this path difference and hence we will obtain our result. Now see, we have obtained delta to be YD by D. Okay. Now we have obtained two kinds of interference here. For constructive interference, my path difference comes out to be even multiple of lambda by 2. So this part difference is equals to the even multiple of lambda by 2. This has some different mathematical expression. We will also derive this situation, that how in case of constructive interference this part difference came out to be even multiple of lambda by 2. Now the value of this delta is y d by d is equals to 2n lambda by 2, or you can say n lambda. So this y is indicating the position of nth fringe, so we write it as yn. So the nth position of the fringe, bright fringe, came out to be n lambda d by small d. Okay, so for fringe width, what we need to evaluate? We need to evaluate the gap between the two locations. Earlier in the diagram, or you can say earlier in the visual, what you have seen, between two bright fringes you were having the width of dark fringe. So from here, so this is the location of your bright fringe. So when you will subtract two locations, yn minus 1, so you will obtain the fringe width of the dark band, fringe width of the dark band. So just evaluate it, yn minus 1. Otherwise you can also write it like y2 minus y1. So again the result will be same. So after subtracting you will get this value, lambda d by d, and we indicate it with symbol beta. So this is the fringe width of a dark band. Okay. So next condition for destructive interference also. Now in case of destructive interference, this path difference came out to be odd multiple of lambda by 2. How it is equal? We will further derive it in separate expression. Okay. So for here we are just using this result. So my path difference came out to be yn d by capital D. So from here the position of nth fringe, so here we are indicating it with yn dash. So we are writing it 2n plus 1 lambda by 2 into d upon small d. Okay, so this is my value for the nth dark fringe. Okay, so by evaluating yn dash minus yn minus 1 dash, so we will get fringe width for the bright fringe. Here n is allowed from 0 to n. Okay, some books write here as 2n minus 1. So in that case n0 is not allowed. Okay, some books are writing 2n minus 1 here. So in that case n0 is not allowed. Here we are mentioning 2n plus 1. So here 0 is allowed. So both the cases are correct. There is no need to get confused. Okay, so once you will evaluate this beta dash, so what you will get? Again the result which you will get will be equal to y capital D by small d. So now this is the expression for fringe width. So from the obtained expression, what you have analyzed, that the fringes which you are obtaining having the same fringe width, that is beta is equals to beta dash. So what does it indicate? That alternatively you are getting a dark fringe and bright fringe of the same width. So bache, this expression is very much important, and also the numericals based on this formula for the fringe width are very much important. So do not leave them from board point of view. Now we are proceeding to the next topic. So अब इस topic के अंदर now we are going to derive the conditions for constructive and destructive interference of light. Like we have written there that path difference is equals to even multiple of lambda by 2 or odd multiple of lambda by 2. From where that came, now we are going to show that. First of all, what we are having, so we are having here two slits. One is S1 and one is S2. Okay, so here two waves were interfering with each other at point P. So this was our condition. So we consider that ray of light coming from this source S1 is given by equation A1 sine omega t minus kx, and the ray of light originating from second source is given by a2 sine omega t minus kx plus phi. Now this phi is the phase difference existing between these two waves. So why we are adding phase difference in the second wave? Because the path travelled by the second wave is the longer one, and moreover the phase difference is given by 2 pi by lambda into path difference. So if addition will be the path difference, then additional will be the phase difference. Otherwise, if you want to make this phi in the y1, then you have to write it here in the subtraction minus phi. Okay, so we are writing here in the second, so we are writing it in plus. So now see, according to the superposition principle, so y is equal to what? Y is equal to y1 plus y2. So here y1 is given by a1 sine omega t minus kx plus a2 sine omega t minus kx plus phi. So now here consider this omega t minus kx as a separate term and this phi as a separate term. Now here we will apply the formula sine a plus b. So it will be sine omega t minus kx plus a2 sine a cos b plus cos a sin b. Okay, so here this sin omega t minus kx, and in this term sin omega t minus kx is common, so we indicate it like this: a1 plus a2 cos phi into sin omega t minus kx, and rest of the term we can write here as a2 cos omega t minus kx into sin phi. So here this sin phi and this a2, so we are considering this term as r sin theta and we are considering this term as r cos theta. Okay, so just see what happens. Say this a1 plus a2 cos phi is written as r cos theta and a2 sin phi is written as r sin theta. So let this be equation 1 and let this be equation 2. Now squaring and adding equation 1 and 2. What you will get? You will simply get here as r square is equals to a1 square plus a2 square plus 2a1 a2 cos phi. Okay, so you will get this. Now what is this r? This r is now the amplitude of the superimposed wave. So the wave generated after the superposition of S1 and S2 is having the resultant amplitude to be r. Here a1 and a2 are the amplitudes of waves generated from S1 and S2. Also intensity is proportional to amplitude square. So using this formula now we are arriving to the new result. Now we have obtained this formula: r square is equals to a1 square plus a2 square plus 2a1 a2 cos phi. Okay, and moreover we know intensity is proportional to amplitude square. So here you can write I is equals to kr square and I1 as ka1 square and I2 as ka2 square. Here k is proportionality constant. So this expression will be reduced to I will be equal to I1 plus I2 plus 2 square root of I1 I2 cos phi. Okay, So here the term I will be maximum if cos phi is maximum, that is plus 1. So this is only possible if phi is equals to 0, 2 pi, 4 pi, even multiple, or you can say that phi is equal to 2n pi. Okay, and this is phase difference na, so path difference is equals to 2 pi by lambda into, sorry, this is phase difference. So phase difference is equals to 2 pi by lambda into path difference. So phase difference came out to be 2n pi is equals to 2 pi by lambda is equals to into path difference. So here 2 pi cancels with this 2 pi. So what you are getting here, that path difference is equals to n lambda, or you can say that even multiple of lambda by 2. So both are the same thing. So this is the condition for maxima where you will get the maximum intensity after superposition. Okay bache. So now in the similar way we are proceeding for the minimum intensity. So expression for obtained intensity is I is equals to I1 plus I2 plus 2 square root of I1 I2 cos phi. Okay. So now I will be minimum if cos phi is equals to minus 1, the minimum value, which is only possible if your phi is equal to 2n plus 1 pi or 2n minus 1 pi. Okay. Now path difference we need to evaluate. So path difference into 2 pi by lambda is equals to phase difference. Now phase difference is 2n plus 1 pi, and here path difference we need to evaluate. So we product it like this, lambda by 2 pi. So this pi cancels with this pi. So here path difference came out to be odd multiple of lambda by 2. So this is how we have obtained the condition for destructive interference, that path difference should be equal to odd multiple of lambda by 2. I hope this is clear to you. So that's all students. So this is what we have covered the section interference today. See, now I am going to show you the variation of intensity on the screen with the phase difference. See, at the odd multiple of pi you are getting a minima everywhere. See, odd multiple you are getting minima, and moreover at the even multiple you are getting maximum, and moreover you can clearly see that if you try to plot the value maximum intensity and minimum intensity, maximum intensity you can write here as a1 square plus a2 square plus 2a1 a2. Cos phi we are taking 1 for maximum, so that's why here you will write a1 plus a2. So clearly your intensity is independent of phase difference. So if a1 and a2 are equal, so I max can be written as 2a square, or you can say 4a square. कहीं भी maxima आएगा तो उसका amplitude आएगा 4a square और minima का amplitude 0. Any confusion in this? Okay. So with this, now we are going to end our session here. So thank you students for watching this video. So if you are having any doubt in any concept anywhere in the video, so you can leave that doubt in the comment section. So see you again students in the next video, in which we will cover the section diffraction. God bless you all.